So first I will talk about the introduction of monocytes. This is a picture of monocytes. Monocyte is a type of leukocyte or white blood cells and also precursors of tissue macrophages. Monocyte found in all vertebrates and can remain in the circulation for up to 1 to 2 days. After which time, if they have not been recruited into tissues for facing a danger, they die and are removed. Monocytes originate in the bone marrow from hematopoietic stem cell (HSCs) and develop through a series of sequential differentiation stages. The common myeloid progenitor (CMP), the granulocyte macrophage progenitor (GMP), the common macrophage and disease precursors (MDP), and finally the committed monocyte progenitor (CMOP). Monocyte contain eosinophilic granule, it's dark blue, well developed, Golgi and many lysosomes. They are not only important in the immune system ability to destroy invaders, but also in facilitating healing and repair. Monocyte acts as antigens, presenting cells for all the white blood cells and release chemotoxic chemicals which cause all the white blood cells to the site of a panel. Next is the structure of monocytes. Monocyte is like cells of the blood, have 10 to 18 micrometer in the diameter. They have a typical morphology features such as irregular cell shape. Monocytes have a granulated cytoplasm. They also have containing chromatin nucleus. Monocytes have abundant low-grade cytoplasm. The cytoplasm contains like number of 5 granules, which often appear to the more numerous near the cell membrane. These granules may be difficult to see if the blood film is poorly stained. The nucleus is eccentric or central, has overall kidney shape, and it indented and pale.
This part, we first need to know about innate immunity. Innate immunity is relatively non-specific. It is the body's first-line defense against many bacterial pathogens. Innate immunity resides in the skin mucous membrane, polymorphonuclear cells, complement system, and a select group of cells that possess cytotoxic capabilities. Monocyte can differentiate into different kinds of cells depends on which tissue monocyte transfer into. For example, monocyte in the brain will differentiate into microglia, while in the liver it will become purpose cell, etc. Stem cell in bone marrow, when transferred to the blood, will become monocyte, and when transferred to tissues, depends on environment stimuli, it will differentiate into macrophage or dendritic cells. About macrophage, monocyte is circulating while macrophages are fixed in lymphoid and mucosal tissue. They can also phagocytose foreign microorganisms, binding to complement to a foreign substance or antigen, amplifying the body innate immunity system by means of its role as an opsonin or as a chemoattractant. Macrophage differentiation from monocyte occur in the tissue in concomitant with the acquisition of a functional phenotype that depends on microenvironmental signal, thereby accounting for many and apparently opposed macrophage function. Monocyte will combine with the GM-CSF or granulocyte macrophage colony stimulating factor, and interferon gamma and TNF alpha are interleukin 4 and interleukin 13. If it combines with the GM-CSF, it will become M1 macrophage, while combined with the interleukin 4 and interleukin 13, it will become M2 macrophage. Dendritic cells, monocyte can differentiate into dendritic cells by adding to the cytokinin granulocyte macrophage colony stimulating factor, or in short of GM-CSF and interleukin-4. About the phagocytosis, as I have mentioned above, monocyte will differentiate into macrophage, and macrophage will help us to eat up on the bad thing that they try to invade into our body, which we call it phagocytosis. And monocyte can perform phagocytosis using intermediary proteins such as antibodies or complement that code the pathogen, as well as by guiding the microbe directly through pattern recognition receptor that recognize pathogen. Monocytes are also capable of killing infected host cells through antibody-dependent cell-mediated cytotoxicity.
So this following part will be about the function of the monocyte in the adaptive immune system. So a monocyte although is a cell of the net immunity, but it can have function in the adaptive immunity because it can interact with the helper T cell and as a consequence will activate the B cell and inducing the cytotoxic T cell proliferation. So all of the monocyte phagocytic systems are antigen presenting cell, which means they can engulf antigen and present them on the MHC LAT2 protein on the surface membrane, and that protein is crucial to activate the helper T cell. So there are the key signal for the T cell activation. First, it needs to adhesion, and then two crucial signaling molecules for the T cell activation are the antigen specific activation from the T cell receptor and the antigen epitope on the MHC LAT2, and another is the co-stimulation signal from the P7 of the antigen presenting cell to the CD28 of the T cell. So although all of the monocyte phagocytic cell can activate the T helper 1 T cell, but I will give the example of the dendritic cell because this is the best cell for activating T cell. The dendritic cell were located under the epithelial layer, and it's a sentinel for under the skin, and when it's activated by the antigen, it will travel to the lymphatic through the lymphatic vessel to the lymph node, where there are constitutive T cell coming through there, and then when it activates the T cell in the lymph node, the T cell will then activate the B cell or the cytotoxic T cell, and then return back to blood vessel to the infectious site to fight off the pathogen. Here's the close-up of the process. The dendritic cell coming to the lymph node through the lymphatic vessel over here, and it's coming through to the paracortical layer, where the T cell and B cell will coming into from the high endothelial venules. In there, the T cell and will interact with the activated dendritic cell, and when there is a match between a T cell and the dendritic cell, it will activate the T cell, and then the T cell will proliferate and travel back to the blood through the artery vein and go to the infectious site. Also, the antigen presenting cell can induce the T cell proliferation via two pathways. The first pathway is the APC will engage with a virus, process and present part of the antigen on the MHC class 2, which will interact with the CD4 T cell, and then the CD4 T cell will activate the cytotoxic T cell. Also, it can activate the cytotoxic T cell via cross presentation. In short, the dendritic cell will pick up the antigen from virus infected cell, and it will process it and present it on the MHC class 1, which will directly interact with the cytotoxic T cell and activate it.
Monocytes play critical roles in the maintenance of health. Consequently, the increased production or absence of monocytes results in diseases. The increase in the number of monocytes circulating in the blood is called monocytosis. Monocytosis is associated with stress or with subacute or chronic inflammation in diseases such as endocarditis, is the inflammation of the endocardium, or tuberculosis, or protozoan infections, and etc. This is the most common cause of monocytosis. Monocytosis can be the cause of many diseases. For example, it can lead to an increase in risk of atherosclerosis, which could lead to heart attack, stroke, and heart failure, because monocytes accumulate in blood vessels and contribute to the development and rupture of atherosclerotic plaque, causing a blockage in blood vessels. Monocytosis may also involve in the risk of death in the elderly. Research shows that the increase in number of monocytes is associated with an increased risk of cardiovascular and cancer-related risk of dying in the elderly. On the other hand, the deficiency or absence of monocytes in blood circulation is called monocytopenia. Monocytopenia may occur reference to a variety of medical conditions. They could be a deficiency of vitamin B12. Vitamin B12 is a critical ingredient in the production of monocytes and other white blood cells. Insufficient vitamin B12 would indicate that you are likely to suffer from monocytopenia. Monocytopenia may also occur in unhealthy bone marrow. Bone marrow disorders will significantly affect the production of monocytes, and their count would go below average. Some medical conditions have been found to be the basis of bone marrow disorders. For example, hairy cell leukemia, rheumatoid arthritis, aplastic anemia, lupus, HIV/AIDS, tuberculosis, etc. Monocytopenia results in the increase of susceptibility to infections, which could lead to many diseases and syndromes, such as cervical cancer. Due to progressive monocytopenia, patients with primary immunodeficiency are susceptible to severe persistent human papillomavirus, or HPV, infections that can cause cervical cancer. Monocytopenia is also associated with monomach syndrome. This recently recognized but rare disorder has the complete absence of monocyte. The syndrome is characterized by increased susceptibility to mycobacteria, fungal, and human papillomavirus infection. The cause is a gene defect that affects the bone marrow. Symptoms vary depending on the specific microorganism that causes the infection. Patients have an increased chance of developing malignancies and may develop autoimmune phenomena, including lupus-like syndromes, or primary biliary cirrhosis, or aggressive multiple sclerosis.
Thank you for your listening.